All right, there was a question in chat that I want to address to everybody. So the question was, what's the material going to be on the final exam? So the final exam is the material after the midterm exam through chapter 12, so through the end of the course. So ANOVA and chi-squared goodness of fit and test for independence will be on the final exam, but the problems I think will be pretty straightforward examples from those sections. So you can get a pretty good idea what the problems will be like from the sample final exam. And that is actually available now on my stat lab. So I posted that yesterday. So the last 3 class meetings are going to be, last 4 class meetings we have today also. Today's plan: finish hypothesis testing, cautions and pitfalls, that presentation that we started last time, start correlation and regression. And then next week, continue with correlation and regression, then finish correlation and regression and do some Excel demos for correlation and regression. Perhaps start chi-squared goodness of fit or independence, goodness of fit test / test for independence. And then Monday the 6th, we do have a normal class meeting Monday the 6th, and there we'll do an overview of we'll continue our overview of chi-squared goodness of fit, chi-squared test for independence, and ANOVA. Because the final exam is the week of Friday the 3rd through Friday the 10th, and obviously we won't have completed Monday's class really in time for that window. I'll post a supplement on chi-squared goodness of fit and on ANOVA to YouTube, so that way if you want to if you want to watch those couple of supplements, work the homework, and then take the test, take the final exam early, you're certainly welcome to do that. That also, if you choose to use that to free up your Monday, if that works a little better for you as we get to kind of crunch time and time management becomes a little trickier with all of the different things that are due, you can feel free to do that too. So that Monday we'll just be covering material, but like I said, I'll post a couple of supplements that cover the same material. Wednesday the 8th, we have an optional review session from 10:30 to 12:30. So if you want to pop in, if you have any questions, I wouldn't recommend taking the exam much later than Wednesday the 8th. It's due on Friday the 10th. There are no due date extensions, just out of fairness to the rest of the class, and because I have to get grades turned around and entered pretty quickly. So don't wait until Thursday or Friday to take the exam. Plan to take the exam a bit earlier. I would say Wednesday at the latest, and that way if something goes wrong, you have a buffer, you have some margin. If a technological issue needs to be worked out or a personal issue comes up or something, you have a little bit of buffer there. Obviously, in the case of something really extenuating, there are other options like an incomplete grade that can be completed later on, but that would be like, oh, I was in a car crash on Tuesday and I'm going to be in the hospital for 4 days and can't take the exam, or something like that. It would have to be quite an extenuating circumstance. So that is an overview of what's up for the rest of the course. And like I said, the sample final exam is now posted, so that should give you a pretty good idea of what's going to be on the actual final exam. I would recommend taking the sample final exam in a similar way to how you're going to take the actual final exam. So sit down in the same location that you're going to take it in, give yourself the same amount of time, give yourself the same resources, calculator, formula sheets, etc., and take it as if you were sitting for the final exam. What that'll do is that'll give you kind of on your first look at the sample final, that'll give you an idea of maybe what problem types you might struggle on, what might have taken you longer than you would have liked, and that might help guide your study. You can take the sample final as many times as you want. So, after you go through that first attempt and that kind of guides your study a little bit, you can pop back in and then look, retry this problem or review that topic or something like that whenever you want. But at least for the first time, I would recommend you take it that way. I think that'll help guide your studying for the final exam. So are there any questions on anything before we get into the material for today? Yeah, I think I addressed the questions in chat. All right. So we're going to continue with our hypothesis testing cautions and pitfalls discussion. So let me just get my Windows reset up here. I'll pop the PowerPoint into the chat. I don't know what's up with my voice this morning. Oops, I accidentally sent that as a DM to somebody. There we go. I popped this PowerPoint in the chat just in case you don't have it. One more second while I get my windows all realigned and ready to go. Okay. Just give me 1 second. Okay, so remember from last time we were talking about some cautions and pitfalls of hypothesis testing, particularly when it comes to the interpretation of the results of the hypothesis tests and maybe some of the choices that are made along the way. One of the things that we discussed last time was significance versus relevance, very important idea that we can have a highly statistically significant result, but especially when we have big data, when we have a large sample size, it could be of minimal relevance. We might not care about it. The effect size could be very small. Maybe it's not a big enough effect size for us to make any qualitative difference on our understanding of the world or on our course of action moving forward, but it's highly statistically significant. So we don't want to conflate the two ideas of statistical significance versus practical relevance. Sometimes the two are aligned, but sometimes they're not. So we want to make sure that we understand that. Just having a very small p-value does not mean that this is a very, very important result for our practice. We also talked a little bit already about how it's kind of industry standard to just peg alpha at 5%. We typically kind of think that that means beta is around 20%, at least in the medical literature. And, we kind of go with that. But we also have discussed that sometimes we recognize that a type 1 error is more costly, much more costly than a type 2 error. Maybe we would want alpha to be even lower. Sometimes a type 2 error is much more costly. Maybe we want beta to be lower and we accept a higher alpha. Maybe we just say, well, alpha and beta are both errors. Can we find a way to minimize the total error? So what should our approach be here? We might be interested in asking that question. Now, I mean, practically speaking, if you write a paper and you're going to publish it in a journal and they say we use alpha equals 5%, well, you're going to use alpha equals 5% because they said so and you want to publish it. But if you wanted to look a little more deeply into this, or maybe even put a note in there, this might be something to think about. Could we minimize something like a cost function of the two errors? Could we minimize something like the cost of alpha, the cost of a type 1 error, times alpha, the type 1 error rate, plus the cost of a type 2 error times the type 2 error rate, beta? Could we choose an alpha and beta to minimize this function relative to these two costs? And of course, alpha and beta are inversely related. So as one goes down, the other goes up. And they're not necessarily linearly related. They're non-linearly related. Okay, so here's kind of it's what I would call kind of a toy example. It's not a real life example, but it's something that approaches a real life example. So let's suppose that we are going to diagnose somebody for diabetes based on a single blood glucose test. Of course, like I said, not real life. The diagnostic criteria are a bit more complicated than that, but we could imagine that this could be maybe a first pass or maybe a screen for diabetes or something. So we're diagnosing suspicion of diabetes, or we could change the details a little bit. And we can imagine two groups of folks. There are the quote normal folks with lower blood glucose levels that are represented by this normal distribution on the left. And then there are the diabetic folks who have higher blood glucose levels on average. They are represented by the normal distribution on the right, the darker red one. And our question is, we want we want a very simple test. We want to measure blood glucose, which is something we can do super quickly, super easily. We want to come up with a number. Maybe that number is 140. And we say, okay, if your test comes up over 140, we suspect diabetes. If it comes up under 140, we do not suspect diabetes, right? We want one number, one cutoff, and that's that. Well, we could set our cutoff quite low. If we set our cutoff quite low, if I say if your blood glucose is over 90, then I'm going to say you're suspicious for diabetes and maybe need further testing or whatever we might say from there. Well, effectively, then we catch all of the diabetics, essentially all of them, right? The people to the right of that line, I'm going to call diabetic. So I effectively call all of the diabetics, but I also call a lot of normal people diabetics, and that's costly, either in terms of hassle or follow-up or anxiety or unneeded treatment. So this is a very sensitive test in the sense that it does capture all of the folks who do have the disease, but it also lumps a bunch of folks without the disease in with those folks and tells them they have the disease. On the other extreme, if we set the bar very high, we call almost no normal people diabetic. So we make almost no errors in that direction, but we also miss a lot of diabetics. We're telling a lot of diabetics that they're non-diabetic. And I can kind of see that if I look on the top left here, if I took this bar and I moved it just a little bit to the right, I would lose a pretty big chunk of orange and pick up a really small chunk of red. Or down here in the bottom, if I took this bar here and moved it a little bit to the left, I would lose a very big chunk of that red air, and I would pick up a small chunk of orange air. I can actually kind of see that when my bar is to either side of this intersection, then by moving the bar closer to the intersection, the error that I lose versus the error that I pick up, that's going to be a net decrease in total error. So you can actually show, it's not super hard to show with a little bit of calculus, that these two errors here, under some reasonable assumptions, are minimized when we choose our cutoff at the intersection of the two curves. So kind of an interesting little detail. If we want to minimize the total error, we and there's a typo in this picture. This isn't my picture. I got this from somebody else, but there's a typo, minimum error. But the total error represented by the sum of these two areas is minimized at the intersection when we choose our cutoff at the intersection of the two curves. And we might be interested in generalizing this idea to say, what if we wanted to minimize the cost function of the errors? Well, that's when that will be minimized whenever the cost times one function equals the cost times the other function. So if the two costs are the same, then we just have this picture and we minimize the cost function of the error right at that same intersection. If the costs are not the same, the minimum of the cost of the total cost of the errors might be at a slightly different point. And just some examples here with something like a jury trial, the standard example for hypothesis tests, usually we say the cost of a type 1 error is much bigger than the cost of a type 2 error. The cost of rejecting the null of innocence and declaring the person guilty when they're actually innocent, we consider that to be a worse outcome than letting a guilty person go free. But for something like, say, a TSA screening, deciding whether somebody getting onto a plane has a bomb on them, if we say, oh, I think that person has a bomb because whatever, detector thing suggested that, and we say, okay, come over here, I want to open your suitcase and look through it, that's probably a pretty small cost relative to the cost of, say, mistakenly letting somebody with a bomb onto a plane. So in that case, our default, our null hypothesis is that the person doesn't have a bomb unless the evidence suggests otherwise. But our barrier for thinking that maybe they do have a bomb, for switching and then investigating further, is probably pretty low, right? Just because the costs are the other way around from the jury trial. Medical tests, it's tough to say. Maybe for a screen, we'd have one approach. For a final diagnosis, we'd have another approach. Maybe it would, maybe our thoughts would change based on how costly or how I can't think of the right word, but like kind of how bad the intervention is. If it's, if you diagnose somebody with this and they have to have a major surgery versus if you diagnose them with it and you say, exercise a little more, eat a little healthier, and come back in 6 months and we'll see if it's gotten better. The severity of the intervention might change for one medical condition versus another. It would be hard to say across the board for medical tests. It would be probably dependent on what you're testing for. Now, this is a huge one here. Misinterpretation of p-values. There's actually the ASA, the American Statistical Association, put out like a paper. It's not quite a journal article. They just published this paper that was like basically how to interpret p-values for dummies. Basically, their argument is like, we're reading all of these papers in journals and people are saying things based on p-values that just aren't true. Like, we really need to clear this up. So I think this is one of the most difficult things in hypothesis testing, interpretation of hypothesis tests, and maybe even across all of frequentist statistics, is that a p-value doesn't say what we kind of naturally want it to say. What we kind of naturally want a p-value to say is really actually a Bayesian argument, and that's actually not what the p-value says. We might be tempted to say something like this. We run our hypothesis test, we do our calculations, we get a small p-value. We get, say, p less than 5%. We reject the null in favor of the alternative. Okay, great, we got a rejection. We might be tempted to say, okay, well, because the p-value is small, then it's unlikely that the null is true. Because I was able to reject the null in favor of the alternative, then the chance that the null is true is low. We might be tempted to say that. Or in other words, we might be tempted to say, because what's the p-value? Well, that's the probability that we would get evidence that looks like this, given the null is true. Remember, that's always the first step in computing the p-value. Assume h naught is true. We look at the evidence we have, the sample we have, and we say, how unlikely or how likely would it be to get such a sample if the null was true? So p-value is probability of evidence, or the sample or whatever, given h naught is true. If the p-value is small, we reject the null in favor of the alternative. But if I'm talking about the probability that h naught is true in light of the evidence, in light of the sample I've obtained, well, that's a probability where the condition is flipped. That was what we spent about a week or so on with Bayes' theorem, right? Is how to flip that condition and what that means. And that's really a Bayesian argument. The frequentist would say, well, either H0 is true or H1 is true. One of them is correct, but I just don't know which one. So but they would say, since one is definitely correct, if I had access to the entire population, I could tell you with 100% certainty which one is correct. So it makes no sense to say the probability that the null is true or false from the frequentist perspective. They're saying one of them is correct, I just don't know which one. But the Bayesian is happy to say the probability H0 is true is this number or whatever. So it's incorrect to say because the p-value is small, then it's unlikely the null is true. It's incorrect to say that because probability of evidence given H0 is true is small, then probability H0 is true given evidence is also small. When we flip the condition, as we saw in Bayes in the Bayes section, we can get very unintuitive results. So what might this look like in our jury trial example? We might be tempted to say, if we're sitting on a jury, oh, well, there's a bunch of circumstantial evidence against this person. So we have some evidence, and we're operating under the null that the person is innocent at the beginning of the trial. And we might say, well, if the person was truly innocent, the probability that all of this circumstantial evidence would line up perfectly in line with that person, the bank robber, they were seen to have this height and this person has the same height. They had red hair. This person has red hair. They got into a blue Toyota Camry. This person owns a blue Toyota Camry. How could all this circumstantial evidence line up against this person if they were innocent? I think it would be very unlikely. Maybe as a frequentist, I then reject the null in favor of the alternative and declare them guilty. So I might say something like this. I might say, I've concluded it's very unlikely for all the circumstantial evidence to exist against this person if they were truly innocent. But if I then make the leap to say, therefore, it is unlikely the person is truly innocent, that's where I've made a logical mistake. I can't conclude that it's unlikely the person is innocent just because, from the frequentist standpoint, I would have enough evidence to reject the null, just because the circumstantial evidence would be unlikely to exist if the person were innocent. Why is that? Well, let's look at an example. So let's suppose that the law is sufficiently well defined that if we had perfect information, we could tell if the person was guilty or not. So we have a null hypothesis, the person is innocent of bank robbery, and the alternative, the person is guilty of bank robbery. Suppose there's a bunch of circumstantial evidence. We estimate that the probability that this evidence would line up against a randomly chosen innocent person from the population, we estimate that it's 0.5%. As frequentists, we would say this is a p-value of 0.5%. This is highly significant. This is significant even at the 1% level, certainly also at the 5 or 10% level. We reject H0 in favor of H1. We declare the person guilty of bank robbery on the basis of this evidence. But what do we usually think of when we say that I've declared a person as guilty? Usually what we think that we mean is, I'm pretty sure that the person is guilty, not I'm pretty sure that it's unlikely for this evidence to have existed for an innocent person, but I'm pretty sure that the person is guilty is really what we're trying to say. Right? Really, the statement we're trying to, that we intuitively or think we're making is a Bayesian statement. In other words, as convincing as this line of logic might sound, when I'm making the decision, I'm not really interested, at least most people I don't think are really interested in knowing how likely such evidence is, but they're interested in making a statement about how likely it is the person is actually guilty. For me to say, I vote guilty or I vote not guilty. Well, for me to say I vote guilty, really what I think I'm saying is that the probability that they are innocent, given the evidence, is less than some small number, or the probability they're guilty, given the evidence, is bigger than 1 minus some small number. If we interpret beyond a reasonable doubt as something like more than 99% likely, so to convict the person, this isn't the same as rejecting at the 1% level, although it might seem so. What's the problem here? Well, one problem is that we've completely left out the prior information. Most people don't rob banks. If we had no other evidence to go on, we consider it extremely unlikely that this person is a bank robber. If you point to a random person on the street and say, do you think that guy's a bank robber? I'd say, no, almost certainly not. Let's suppose that our prior probability distribution before any evidence is considered at a trial is this. Probability of guilty is 0.01%, 1 in 10,000. Probability of innocent is 99.99%. This is in line with the FBI stats for bank robbers, and it's even giving a little more weight to probability of guilty than we ought to, because I don't want to have, too many decimal places floating around. It just gets cumbersome. So what is probability of guilty given evidence? What is probability of guilty given evidence in light of this number here? This probability of evidence given innocent number. Okay, let's find probability of innocent given evidence, which is by Bayes' theorem, probability of evidence given innocent times probability of innocent over probability of evidence. And we could get the evidence in two different ways. We could have gotten this evidence and it matches an innocent person, or we could have gotten the evidence and it matches the guilty person. So the probability of getting this evidence, given that the person is innocent, given that the null is true, is 0.005. That's our 0.5% p-value. That comes up in the numerator and in the denominator. The prior probability of innocent is 0.9999. Again, because very, very few people rob banks. For the second term in our denominator, we see the probability of guilty as 0.001. That's our prior probability of guilty. And let's suppose that if the person is guilty, then all of the evidence will certainly line up against them. So the probability the evidence matches them given they're guilty is 100%. I mean, of course, we have issues like sometimes witnesses remember things wrong or see things wrong or whatever, but let's just suppose this is 100%. Well, note what we're finding. Probability of innocent given evidence is 98%. Therefore, probability of guilty given evidence is only like 2%. So the frequentist would throw the guy in jail based on a p-value of 0.5%, being less than 1%, but the Bayesian would say, but I'm only 2% certain that the person is even guilty. I'm never going to throw them in jail on that. Now, one side note, you might take umbrage with these numbers. Okay, why are we using 0.01% as probability of guilty? I mean, surely if they're sitting there in a trial as the defendant, well, surely their prior probability of being guilty is higher than some randomly chosen person from the street, right? Shouldn't we start with like how many people on trial for bank robbery are innocent of bank robbery or guilty of bank robbery? Wouldn't those be better priors to start with? And I would argue no. And this is why. Because there's a certain body of evidence against the person, right? There's going to be a body of evidence that the police officer used to say arrest the person. That police officer says, I have these 5 points of evidence. They give me probable cause. I can arrest the person. Okay. Then some more investigation is done. The DA looks at the evidence and decides whether to charge. They look at, say, the same 5 points the police officer had, and maybe a couple more points that have come up in the investigation. And they say, okay, I think there's probable cause. I'm going to press charges based on these, say, 5 plus 2 points of information. The judge has to decide whether to let it go to trial. And the judge is going to look at the evidence and going to say, based on these same 7 pieces of evidence, or maybe 8 pieces of evidence now, who knows, I'm going to let it go to trial. So now the person's in trial. Well, and then during the trial, they're going to present the prosecution is going to present those same 7 or 8 or whatever pieces of evidence. Well, if I say, okay, well, given that the person's sitting in the defendant's seat, I should increase their prior probability of being guilty. I'm doing that on the basis of the evidence of those, say, initial 5 points of evidence from the police officer that were considered by the police officer, the DA, the judge, and then I'm going to reconsider them during the trial. I've counted the same pieces of evidence now how many times? It's the prosecution's job to present all of the evidence against the defendant. So the most sensible thing I would argue, and this isn't a statistical certainty, this isn't a mathematical fact, but I would argue that the most sensible thing to do is to initially presume that the person sitting in the defendant's seat is a randomly chosen person from the population. And then the evidence is presented, right? Because that same evidence that the police officer used to arrest, that the DA used to charge, that the judge used to allow it to go to trial, should also be presented at trial. We don't want to count the same evidence 2, 3, 4 times. We should count each piece of evidence once. So we should, I would argue, at the beginning of the trial, if we're the jury, we should look at the person as a randomly chosen person from the population, and then see how the evidence stacks up throughout the trial. Of course, I mean, psychologically, most people don't do that, but that's probably what we should do. Okay, so the frequentist would say, I reject at the 1% level, my p-value is 0.5%, and the Bayesian would say, I'm only 2% certain the person is even guilty under the same evidence. How much evidence will we need? What would the p-value need to be for the Bayesian to agree with the frequentist, for the probability of being guilty to be more than 99% in light of the circumstantial evidence? And we can plug some numbers in. We can see that if we solve this for x, if we set 0.9999x over 0.9999x plus 0.001, this is the same calculation we have here, but we've just replaced the p-value of 0.005 by x. And we're going to say, when is this 1%? Right? When is the probability of innocent given evidence not 98%, but below 1%? And this is approximately 10 to the minus 6. We would need a p-value less than 1 in a million, an extraordinarily highly significant result for the frequentist. We would need that in order for the Bayesian to agree. We would need an extremely small p-value so that when we say, I reject innocence and declare guilt, when I say that, I'm implicitly probably thinking like a Bayesian there. I would need an extremely small p-value in order for my kind of Bayesian thinking to be in line with the frequentist argument. Okay, so what is one of the fundamental problems here? It's that our frequentist argument does not take into account anything about a prior probability, anything about how likely H naught is to be true or false before the evidence is considered. Certainly, we don't think that all null and alternative hypotheses are like equally likely at the outset. Here's a funny example from PhD Comics, XKCD Comics. It's titled, Did the Sun Just Explode? It's night, so we're not sure. So, you know, the light from the surface of the sun takes something like 8 or so minutes to get here. So these people, they have a neutrino detector. It says this neutrino detector measures whether the sun has gone nova. Then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells us the truth. So our null is probably the sun has not gone nova. Our alternative is the sun has gone nova and has exploded. They push the button on it, say, has the sun gone nova? Push the button, it rolls the dice, and it says yes. The frequentist statistician says the probability of this result happening by chance is 1 over 36, right? If both dice come up 6, 1 out of 36 times, that's 0.027 or 2.7%. This is the probability of getting this evidence if the null was true, the probability of getting a yes if the sun has not gone nova. Since that's less than 5%, we reject the null in favor of the alternative, conclude the sun has exploded. And the Bayesian statistician says, bet you $50 it hasn't, right? So it's just pointing out the fact that from the frequentist side of things, we give no respect, I would actually say, to the fact that certain nulls and certain alternative hypotheses from our lifelong experience or from the experience of all of humanity are more or less likely, right? The sun doesn't explode every day. I think that it's very unlikely that the sun has exploded today. On the other hand, whenever trees fall over all the time, if somebody told you that the tree in your backyard fell over and you're not at home, like, you'd be much more likely to believe that, right? As an aside, it's always a good bet to take, because if the sun has exploded, your $50 isn't going to be worth all that much in 8 minutes or so. But so even if the Bayesian statistician lost the bet, the $50 isn't worth it. So but yeah, so I think this points out the issue with one of the issues with hypothesis tests is what we think that we're saying when we say something like I reject the null in favor of the alternative really isn't what we're actually saying. What we think we're saying when we report p-value less than 5% or less than 1% often isn't what we're actually saying. It's very difficult and nuanced to interpret hypothesis tests. I mean, the interpretation doesn't change what the numbers are. You calculate p-value of 0.03 and you get a rejection. Like, that's all a self-contained mathematical system. But the question is, what does that actually mean? What does it actually tell you? What inferences can you make on that? That's where the nuance and the challenge comes in. All right, so another thing to discuss quickly is publication bias, something that we talked about at the beginning of the course. So consider this narrative. Suppose I told you I ran a study where I gave my medication to test subjects who were very ill, and 50 of them recovered within 24 hours. The typical time to recovery for this type of illness is 1 week. Does this represent strong evidence for the efficacy of my drug? Now, if I told you this, I gave my medication to some test subjects, 50 of them recovered within 24 hours, I think just about everybody would have the same question. Well, if 50 out of 50 people got better in 24 hours instead of a week, I think it's pretty obvious this is very strong evidence that my drug seems to be effective, or at the very least that the trial that I'm doing with my drug seems to be effective. Maybe it's a placebo thing or whatever, but there's something unusual going on. If there were 1,000 participants and 50 of them got better within 24 hours, I mean, it kind of seems like that might have happened by chance. The very important idea here is that the number of positive results only tells half the story. The number of negatives is at least as important as the number of positives. And if you think you wouldn't be fooled by a statement like this, I have a friend who's an actuary. My background's in actuarial science. He's an actuary, so he's very well versed in statistics and statistical inference and things like this. Works with numbers all the time. He basically, what actuaries do is they make statistical models for insurance companies to model insurance and to say like what premium should be or what the cost to the policy is, the cost of this policy is going to be for this insured, things like that. So, I mean, very bright guy. But when COVID was coming, really coming to a head, and they were just ramping up testing, and, there weren't quite enough tests to go around. So there was a selection bias as to who was being tested and all of this. He would kind of like every day or every other day, they were always publishing the numbers. Remember that? And he would be publishing these numbers, but only the positives, which is how they were publishing it. And I called him out on it at one point. I said, dude, like you're I mean, I'm not making a political point one way or the other, but you're giving a false impression by just publishing these numbers. The numbers that are available only represent the positives in a sense, not the negatives. There's an inherent bias in these numbers. Now, I'm not saying that there's some kind of conspiracy theory or anything like that, but it's just the idea that the statistics that were available at the time, just presenting those statistics did not represent a full and accurate picture of what was going on. And he actually like argued with me, and he's like, no, this is accurate. And I'm like, so folks who are very well versed in statistics, they can miss this as well. And I'm sure that there have been times in my life that I have missed something like this, and somebody else should have called me out and said, no, that's wrong. And maybe I would have dug in my heels too, I don't know. But we can see pretty clearly from this narrative that the number of positive results only tells half the story. The number of negatives is very important. So if I had one study, if I was reading a journal article, one study that said this, I would say, that's absurd. How many negatives are there? You're only giving me the positives. You're only telling me about the times that it worked and not telling me how many times you tried to get it to work. But what if we zoom out? What if we look at the collection of all studies in a certain field or on a certain topic? Well, the published studies, especially when it comes to, say, medical literature, where you're trying to come up with some new idea that hasn't been figured out before, in terms of the published studies, mostly it's the positive results getting published. If I spend $1 million of research money and do this big long study and it kind of flops, and the thing that I thought was true, that I thought was going to be some revolution in cancer treatment or something, if it turned out to simply not be true, I'm not going to be super proud of that and go and publish it. I'm probably going to try to take my experimental results, take my data that I got, massage it and come up with something else, or take my research in a slightly different direction on the basis of that and get a publishable paper, a positive result in that direction. And even if I did want to publish my negative result, what journal is going to want to publish an article that says, I thought this might be true, I investigated it and it wasn't true? That's not a very interesting thing to publish. So what are the journal articles that get published? The ones with positive results. What are the potential journal articles that don't get published? Often the ones with negative results. The articles that we see when we're looking at a corpus of knowledge, so to speak, that's in the journals in a certain area, represents overwhelmingly the positives, and we don't really know what the negatives look like. We don't know if these 10 journal articles that I found on this in this area, those 10 positives, so to speak, represent 10 positives out of 10 studies or 10 positives out of 1,000 studies. We might also say, okay, well, I mean, if somebody gets a positive result, we might say, oh, like Fisher, we might say, oh, okay, that's interesting. So that's an interesting idea. Maybe my lab will try to verify that. And then kind of either way, it's interesting, right? If we verify what they did, we get a positive result again, and we can bolster that claim. If we get a negative result and we fail to replicate what they did, well, that should be interesting because that cuts against their claim. So that should be interesting. And but is it really prestigious to do that? Are you going to get your full professorship by studying something that's already been studied? Probably not. Are you going to get on the cover of Science by studying something that's already been studied, or by being the one who's breaking brand new ground? It's the latter. So this publication bias can be an issue. There are some journals, but as far as I can tell, not any of the big ones, that have started trying to address this problem and started saying, okay, if you want to publish your end result of your study with us, before you run your experiment, you have to register your experiment with us. All you have to do is just tell us, I plan to do this experiment in this field. This is what I'm going to do. And you tell us ahead of time. And then at the end, you can publish with us if you want to. The idea is that that gets them an idea of how many folks are working on the problem, how many potential papers there would be for publication, how many experiments are being run, and then how many actually get published in the end. But as far as I can tell, none of the big journals do this. None of the most prestigious ones do this. The ones that people would, the ones where it would be most informative because people would really want to publish if they got a really interesting result. So I don't know what the solution to this is, but it's always worthwhile thinking about anytime you read a journal article, this is a positive result. How many negative results were there to offset this positive result? And then kind of lastly, just the general awkward setup of hypothesis tests can also lead to confusion. So if you look at what we do with hypothesis tests, we typically want to show the alternative. So we start by assuming the null. We start by assuming the opposite of what we want to show. We gather some data. We analyze how strange it would be to obtain this data if the null is true, if the other guy's argument is correct. If it would be very unlikely under the null, then we reject the null in favor of the alternative. Very unlikely under the null and more likely under the alternative. If you said, I want to prove that this statement is true, and I said, okay, start by assuming the opposite, and then see if that's in line with the data you collect, you'd probably think I was crazy, right? You might already think I'm crazy, I don't know. But, imagine if you said, I want to show this thing is true, and then I said, okay, here are the 4 steps that you should go through to show that your thing is true. You say, like, why don't I just try to show that it's true? Why would I try to use this backdoor, this essentially a proof by contradiction kind of approach? Why not just use a direct approach? Well, kind of the answer is that we need the proof by contradiction approach because we need enough meat to work with to actually set up all of the probabilities, all of the calculations that we need. By assuming that H naught is true, that gives us the center of the distribution, and we can work off of that. And it's also kind of the logic of the frequentist side of things, where the thing that's random is the sample that's collected, the data that we got. The thing that's random is not whether H naught is true or false. The frequentist would say, if we have perfect knowledge, either H naught is true or H naught is false. We just don't know. So there's no probability H naught is true. To the frequentist, that doesn't make sense. To the frequentist, it only makes sense to say that the thing that's random is the random sample we got. That's our evidence. So we can talk about the probability we get a sample like this one or more extreme. That's a sensible thing to say. Okay, just 1 second. Okay, so after I spent maybe roughly a full class period, in some sense, complaining about hypothesis. I hope it didn't come off as complaining about hypothesis tests, but pointing out the downsides and the cautions. Well, you might say, well, why do we use these? Why don't we use something else then? Well, first, there aren't a whole lot of options available. Bayesian analysis, I like Bayesian analysis. I also like frequentist analysis. I think it just depends on what problem you're trying to solve, which one makes the most sense. But Bayesian analysis is seen as subjective because we have to come up with a prior, right? Go back to the bank robber example. What prior should we use? Should I use like the national probability of somebody being a bank robber, or in our city, or in our state? Should I, right, like how far should I go with that prior? Should I say that, maybe most bank robbers are male? So if the accused is male versus female, should I take that into account? before or after, right? How should the priors be set up? It's not easy to set up priors, because basically our priors are something like our prior information through either our life or through kind of all society. And it's hard to say exactly what that information is. You say, okay, well, maybe we can try to do something called choosing robust priors. That's kind of an interesting idea, where the idea is to choose a prior distribution in such a way that that as we gather more evidence, the prior distribution fades to the background most quickly and lets the evidence come to the foreground most strongly. But that's not easy to do. Also, one thing that I don't have on here is that there's historically a status quo of frequentist statistics. And the reason is, well, there are a couple reasons, but one big reason is that Bayesian statistics, especially the way that they're done today to solve practical problems, really uses a ton of computer power. I mean, it uses a lot of computer power in today's standards of computer power. Certainly, even 30 or 40 years ago, these were calculations you'd have to run on a supercomputer at a university somewhere. And 50 or 60 years ago, probably, you probably wouldn't have been able to run the calculations that we need to run these days to get a good Bayesian analysis. And certainly back in 1920, when people were doing these calculations by hand, were calculators. If you said, oh, like, you know, have a calculator computed out, that meant hand it to a person who was going to sit there. Like, calculator was a job that a person did. They sat there and used whatever tables of logarithms or something, and like did all of these operations by hand to get you a number as a result. So yeah, I mean, Bayesian analysis is computationally very heavy for a lot of it. Now, I mean, some of the stuff we did is a little more straightforward, but for a lot of the stuff that's more in line with things like their equivalent of confidence intervals or things related to hypothesis testing or things related to modeling, it can be very computationally heavy. So kind of because computers weren't really around for most of the development of statistics, maybe for half the development of statistics, frequentist statistics, which is a little less, well, sometimes a lot less calculation heavy, what was the standard. Okay. And now I want to give frequentist analysis its due. I think it's very important to say that well-performed and, very importantly, well-analyzed hypothesis tests generate solid results. So it's not an argument that we should never use hypothesis tests. It's an argument that we should consider when a hypothesis test is best to use and maybe when something else might be better. And very importantly, when we use hypothesis tests, we have to be very careful with the analysis and the interpretation so that we don't make these pitfalls. We don't run into these pitfalls. We have to analyze and interpret it very carefully and very thoughtfully, not just, throw out a paragraph that sounds pretty good and then be on our way. We have to be very careful with, okay, I said something about a p-value. I know that that's a tricky situation. Let me think through this very carefully and cautiously, right? Something like that. So if we're very careful in our analysis and interpretation, and we're very careful to convey that in such a way that our reader will also hopefully not be pulled into any of those pitfalls, it can generate solid results. Just as an example, let's suppose that alpha is 5% and beta is 20%, so our power is 80%. Let's also suppose that the prior probability that H naught is true in the Bayesian sense is given by a variable pi. So just like p for base probability, not 3.14, but just using that as the letter p. Then given that H naught is rejected, what is the probability that H naught is false, given that it's rejected? In other words, what's the probability that the Bayesian would say that the null is false, given that the frequentist rejects the null, or roughly speaking, that the frequentist says the null is false? It's given by this ratio here. what is this plot? This is a plot of y, the y-axis, is probability H naught false given H naught rejected. In other words, when y is close to 1, the Bayesian says, yeah, H naught is likely false when the frequentist says reject H naught. When y is close to 1, when we're near the top of the graph, or when our graph is near the top of this window, I should say, the Bayesian agrees with the frequentist. Now, what is our x-axis? This is the actual probability that H naught is false. Or I'm sorry, not the actual, that's the prior probability that H naught is false. Let's look at 0.5 on the x-axis. If the Bayesian looks at the problem and says, I think it's a 50-50 shot, I think it's a coin flip whether H naught is true or false, I don't have a strong opinion either way based on the prior evidence. And then there's enough circumstantial evidence, so to speak. There's a small enough p-value for the frequentist to reject. There's a p-value less than 5%. We can see that our graph is very near the top of the window. It's maybe something like the Bayesian would say that it's about 95% likely that the null is false. Right at 50%, when a Bayesian would say it's as likely that the null is true versus that it's false. When the frequentist rejects at the 5% level, the Bayesian more or less says I'm 95% confident that the null is false. I mean, that actually sounds like what I just said we shouldn't say back in the bank robber situation. But it turns out to be true whenever our probability of H not being false, our prior probability is about 0.5 or higher. Where do we have a problem? Where we have a problem is way on the left over here. If the Bayesian looks at this and says the probability that H naught is false and that H1 is true, I think is very low. I think it's 10%, 5%, 1%, 1 in 10,000. If I'm way on the left of the graph over here, then my graph is very near the bottom of the window. That's where the frequentist would reject the null in favor of the alternative, but the Bayesian would say, but I'm very unconvinced that H naught is false. I think the probability that H naught is false is very low, and it's still very likely that H naught is true. So on the left of the graph here, when probability H naught is false is very low from the Bayesian perspective, say maybe under 20%, that's where we're going to get big disagreement between the Bayesian and the frequentist way of thinking. So again, if we kind of recognize that that's a trouble area, where it seems like H naught from the Bayesian perspective is very, very likely, and H1 is very, very unlikely from the Bayesian perspective, then the frequentist generating a rejection is less convincing for me. On the other hand, if I think that the two hypotheses are about equally likely, or even that H naught is unlikely and H1 is likely from the Bayesian perspective, then if the frequentist generates a rejection, that's quite convincing. That's quite strong evidence, even in the Bayesian sense. So I want to give it its due that as long as we're not in this kind of somewhat pathological situation where we're quite certain, say 80% or more certain that the null is true, unless we're in that situation, the Bayesian results and the frequentist results kind of more or less agree. In the sense of like, would you declare the person guilty? You know, as long as we're kind of somewhat off to the right of the picture here, I think when the frequentist says yes, the Bayesian would also say yes. So some practical takeaways. So remember that there's a publication bias. The unpublished insignificant results are often at least as important as the published and significant ones. And what I just mentioned is we have to be very, very careful about interpretation of p-values. We don't want to be in a frequentist setting and start talking about the likelihood that the null or alternative hypothesis is true. Any questions on anything that we've talked about, either in this PowerPoint or at all in hypothesis testing? All right, let me get my screens reset up here. Give me 1 second. Okay, so moving on to our next topic, we have kind of 3 topics left in the course: correlation regression, chi-square tests, and ANOVA. And for all 3 of them, or well, really for correlation regression and ANOVA, we're just scratching the surface. I guess the chi-square tests we're covering reasonably thoroughly. But for these 2 topics, we're just scratching the surface. Correlation regression is a topic that you could easily take a full semester course on, and you could probably take a 2 or 3 or something semester graduate level math or stats course on correlation regression. So this is a huge topic that can be studied very deeply and very broadly. Of course, we're just scratching the surface here. There is a book called Undergraduate Econometrics by Hill, Griffiths, and Judge. I think I might have mentioned it at the beginning of the course, and I think it's on the Blackboard site under some supplementary material, or some maybe on the syllabus under supplementary books if you were interested. And so for folks going into something like finance or economics or something like that, might be an interesting book to pick up. It kind of goes into correlation regression at a half a level above what we are doing here. It has a little bit of calculus in it, but they've specifically written the book so that you can skip the calculus sections and you're not really losing very much. So if you want a little more on correlation regression, you can read through our book a little more carefully. I'm kind of hitting the high points here. And you can pick up that undergraduate econometrics book. That would be a good, kind of next resource. Sorry, give me 1 more second. Sorry, I'm trying not to sneeze into the microphone and blow all of your ears out. So I always have this week or so, usually one around spring and one around fall, where my allergies are just haywire. Okay, so intro to correlation regression. The goal of this chapter is to study the relationship between 2 variables, x and y, and in particular the linear relationship. And our data is ordered pairs. So my data looks like data point 1 is like x1, y1, data point 2 is like x2, y2, and data point n, xn, yn, where these are ordered. In other words, a classic example might be something like the x variable being a person's weight and the y variable being their height. So I would take person 1, I would measure their height and their weight, write that down. Those both correspond to person 1. So maybe this is the point x1 comma y1. For person 2, I do the same thing. Maybe this is point x2 y2. And I do this for a bunch of different people. I have, say, through point xn, yn up here. And this gets me a scatter plot. It gets me a two-dimensional representation of this data that relates the variables x and y. So this is what my data set will look like. It'll look like either a list like that or graphically like a scatter plot like I have over here. And my kind of end goal is to fit a model. We'll call it y hat equals alpha plus beta x, a linear model. We're studying the linear relationship between the two variables. This is a line in these two dimensions, and if I overlay this line on top of my data for a suitable choice of alpha and beta, maybe it looks like this. And the idea here is that understanding and interpreting a linear model that just has an intercept and a slope, that's much easier for me to understand and interpret and to use to make predictions than these maybe 10 or 100 or a million data points. So this is in some sense a descriptive model saying what's the line of best fit, what's the best linear model for this data. But it's also in some sense an inferential model that I can then ask, once I find the best alpha and beta to use, then if I'm interested in a different x, if I'm interested in this value of x over here, what's my estimate for y? Or if I'm interested in a value of x, say here, that maybe falls in between some data points, I can have an estimate there also. I can have an interpolation or an extrapolation. I can either go within my data set, kind of fill in some of the missing, some of the gaps in a sense, or I can go outside of my data set and make guesses about how things are likely to propagate when x is larger or smaller than any of the x's I've seen so far. As kind of a general rule, interpolation, going inside the data set and making inferences, is more reliable than extrapolation, going outside of the data set. But this is kind of our end goal here. This is what regression tries to do. But before we understand regression, we want to understand correlation. And correlation is also a nice tool in its own right. Okay. Getting my papers lined up over here. There we go. Okay, so let's talk about correlation, or the correlation coefficient. The correlation coefficient gets two notations, one for sample, one for population. The sample correlation coefficient is R, just the usual Roman letter R, or the American letter R. And the population is this letter that looks a little like a P with kind of a curly tail. It's the Greek letter rho, or the Greek letter R. So it looks a little like a P with a curly tail, or for whatever reason, the math equation editor version looks a little funky. I don't know. But usually you would write rho like this. Like the tail would be kind of pointing off to the right. Theirs was kind of pointing off to the left. It looks a little strange, but whatever. So just like before, the sample statistic is like an American letter and the population parameter is a Greek letter. For our purposes here, I'm not going to be super careful about when I use the sample versus the population, when I use R versus rho. I'm going to be using them more or less interchangeably. So by definition, it's a mathematical certainty that either a sample or population correlation is in the interval -1 to 1, including the endpoints. The way that it's calculated, this has to be true. So what is the goal of correlation? It's to describe the degree and nature, or maybe the strength and direction, something like that, of the linear relationship between the variables. And there are two characteristics that we're interested in: the magnitude. The magnitude is the absolute value. It's between 0 and 1, including the endpoints. And the sign, it can be positive or negative. So let's look at each of these independently. So the sign indicates whether we're positively or negatively related or associated. If the sign is positive, that suggests that higher values of x are associated with higher values of y, and vice versa. Let me move this one down a little bit. And that lower values of x are associated with lower values of y. Now, it's a little bit of a pet peeve of mine that people often say, as x increases, y increases, and as x decreases, y decreases. We're actually not saying that at all, because x increasing means we start at a point and then we move forward in something like in time or something like that. But that's not what we're saying. We're saying we have a snapshot. We have lots of different, let's say, lots of different people, and we've measured their heights and weights. And I know that it's a different thing to say that, for instance, that I know that heavier people tend to be taller and lighter people tend to be shorter. That's one statement. If I make the statement that, you know, as weight increases, height tends to increase, or as weight decreases, height tends to decrease, that could kind of mean a couple different things, right? One way of interpreting something like that is if your 6 foot tall, 230-pound neighbor goes on a diet and loses 20 pounds, I expect their height to decrease. Well, no, that's not what I'm saying at all. I'm just saying that taller people tend to be heavier and shorter people tend to be lighter. I'm not saying anything about increase or decrease, say, over time. It can be, the nuances can be difficult if I start talking about increasing or decreasing. Sorry, give me 1 second here. So personally, I don't like saying when x increases, y increases, or when x decreases, y tends to decrease. I like to say it this way, that higher values of x are associated with higher values of y, lower values of x are associated with lower values of y when the sign is positive. When the sign is negative, just the opposite. Higher values of x are associated with lower values of y, and lower values of x are associated with higher values of y. So if there's a relationship, if there's a linear relationship between the variables, the sign tells us something about the nature of that relationship or the direction of that relationship. Now the magnitude is between 0 and 1, remember. If it's near 0, that suggests a very weak linear relationship or weak evidence of a linear relationship. So the strength of the linear relationship between x and y seems to be quite low. On the other hand, if the magnitude is near 1, that suggests strong evidence of a linear relationship, or a strong linear relationship between the two variables. So if my magnitude is near 0, I don't really care about whether the sign is positive or negative. Negative 0.1 or positive 0.1 correlation, either way, we don't have much in the way of a linear relationship. So whether it's positive 0.1 or negative 0.1 isn't a big difference. Sorry, give me a sec, one more time. I guess I'm just allergic to correlation and regression. I don't know. I was doing fine during hypothesis testing. So yeah, if magnitude is near 0, we don't care much about the sign. Because there's weak evidence of a linear relationship, I don't really care what we're suggesting that the nature of that relationship is, because I don't think that such a relationship exists in the first place. But when we have a strong evidence of a linear relationship, I think that that the relationship does exist. Now I very much care about the nature. I very much care whether my correlation is like positive 0.8 or negative 0.8. That tells me a lot, because I think there is a strong linear relationship between the variables. So now the nature of that relationship becomes important. So we really kind of have 3 scenarios combining these two together: near negative 1, near 0, and near positive 1. These are like my 3 different scenarios that I'm interested in. Near 0, whether we're a little positive or a little negative, we just say that's weak evidence of a linear relationship between the variables. Near -1, strong evidence of a linear relationship, and it's in kind of the opposite sense. The nature of that relationship is that higher values of x are associated with lower values of y and vice versa. And a correlation near +1, again, strong evidence of a linear relationship, but now kind of in the same direction. The nature is that higher values of x are associated with higher values of y and lower associated with lower. So these are kind of our 3 scenarios of interest. Okay. I'm going to open up an Excel file here. Okay, so here I have some stock data. I have a scatter plot, and I have a correlation. So we might ask, well, okay, given a data set, here I have a certain day, I have the paired prices, gold and Google on that day, a different day, I have going to Google on that day. How can I compute the correlation coefficient? Well, it turns out that it's kind of an annoying and cumbersome calculation to do by hand. So we're going to be relying on Excel to do these computations for us, both in correlation and regression. These calculations are just very annoying to do by hand. We'll do them on the computer. If I look at gold in Google and a scatter plot, I see that it's just kind of like a blob of random points, it looks like. It doesn't look like there's a strong linear relationship, right? It doesn't look like something like this, where a straight line would seemingly be a pretty good model. If I tried to draw a straight line through here to be a good model of this data, I don't think I could find a straight line that you could convince me was actually a good model of what's going on in this picture. So at a glance, it kind of seems like the nature, or sorry, the degree of the linear relationship is very low. And I'm not really interested in the nature of it. I'm not really interested in whether it's positive or negative in nature, because I don't think there's much of a relationship at all. To calculate the correlation coefficient, I use my Excel function CORREL, correlation. And then I enter in the list of the X's along with the list of the Y's. And Excel expects these to be paired off properly. So you can see how these two lists kind of line up nicely like this. And when I compute that, I see I get negative 0.014. 0.01 on a scale of 0 to 1, that's about as close as you can get to 0. So our correlation coefficient confirms our suspicion that there doesn't seem to be a very strong linear relationship between these two variables. And as an aside, Google is just Google's stock price, and GLD is Spider Gold shares. So this is more or less the price of gold for some small increment of gold. So maybe at the time it would, maybe this, you could think of this as something like 1/10 of an ounce of gold or something. But really it's just like a stock kind of thing that you can buy, that all that they do is they buy gold and just keep gold in a vault somewhere. So it's like buying gold, but you don't have to worry about storing it or any of that. So this also kind of qualitatively makes sense. I don't really expect that the price of gold is going to move like the price of Google moves. What about gold versus Microsoft? Kind of a similar thing. It looks like just a blob in the scatter plot. I don't think I could really draw a line through this that would do a good job of modeling most of the data. If I compute my correlation, I see that it's negative 0.086. 0.08 is pretty close to 0, not very close to 1. So again, I think that there's a low degree, a weak degree of linear relationship between the two variables. I don't think there's much of a relationship at all. I'm not interested in whether any potential relationship is positive or negative, just no relationship here. What about Google versus Microsoft? Well, they're in kind of the same sector. Maybe I think that for them to be related a little bit more. But if I look at their share prices, actually, the evidence doesn't really back that up. I might have expected that, but that's not what I see in the scatter plot. Again, it doesn't look like I could draw a straight line anywhere on this picture that would do a good job of modeling most of the data. Any line that I draw is going to do a good job for some of the data and a terrible job for some other of the data. Again, I see my correlation negative 0.32. On the scale from 0 to 1, 0.3 is still pretty close to 0. I probably still would say that there's a low degree of linear relationship between these two variables. And I'm not so interested in the sign of the relationship. What if we get closer together, Google versus Yahoo? Both search engines, both doing something pretty similar. Well, now I see something in the scatter plot. It does look like I could draw a straight line here. Let me me pop this over here. Can I just paste it? Good. It does look like maybe a line something like this. That might be a straight line that's pretty close to most of the data. That does a good job modeling this data. I might think at this point, okay, there does seem to be a decent degree, a strong degree of linear relationship between these variables. I look at my correlation coefficient and it's about 0.8, positive 0.8. So it does seem like there's a strong degree of linear relationship in absolute value. This is closer to 1 than to 0. And now I do care about the nature. The nature is also positive. So on days that Google's stock price is higher than usual, Yahoo's stock price also tends to be higher than usual. And vice versa. On days that Google stock price is lower than usual, Yahoo's tends to also be lower than usual. And then lastly, let's look at PIMCO versus Microsoft. Well, here we have, again, maybe somewhat of a linear relationship. It doesn't seem as nice as the Google versus Yahoo, but maybe I could imagine a line going something like this. And I mean, there do seem to be a couple points here and there that are kind of far away from that line, but it seems like a lot of the data would fall fairly closely to a line that I might draw, that I could pick a line that's a pretty good model for this data. And again, I see a correlation that's 0.69 or so. That's a good bit closer to 1 than 0. So I think that there is indeed a strong linear relationship between these two variables. And the nature of that linear relationship is positive, that when Microsoft is higher than usual, PIMCO is also higher than usual, and vice versa. And as an aside, Microsoft is a stock. It's a company that you can own shares of course. And PIMCO is actually a bond portfolio. So folks that are in, I think we have some folks who are in finance and accounting, those kind of fields, you might say, wait, I thought bonds and stocks kind of move opposite of one another. That kind of when one is high, the other tends to be low and vice versa. I thought that they would have a negative relationship if they had a linear relationship at all. And interestingly, that's usually true, but this is PIMCO's high yield portfolio. So these are bonds that this is debt for companies that are kind of not in the best financial situation. So when the market overall is doing well, that's when the stocks are doing well. Very high grade bonds like GE or somebody like that, or government bonds, they go down because I pull my money out of those boring investments that don't yield a lot in order to put it into the hot stock market and get more return over there. But for something like a high yield bond, a bond for or debt from a company that is a little shaky in their finances, that debt's actually worth more in a good economy because that company is less likely to go under in a good economy. In a bad economy, when the stocks are down, that's when that company's debt is much less favorable. They're much more likely to go bankrupt in a bad economy and not be able to satisfy their debt obligations. So these high yield bonds actually look more like stocks than normal bonds. So just interesting little tidbit there for my folks interested in finance. Okay, so we've seen some examples. Now for the last 10 minutes or so, let's do a little bit of practice and then we'll call it a day. Waiting for this Excel to load. There we go. Okay, so here I have 5 scatter plots and I have 5 correlations. Now, it would be unfair of me to say, like, point to this scatter plot and say, what's the correlation? That's not reasonable. But I have 5 scatter plots with 5 correlations that are sufficiently different from one another. We should be able to tell which one's which by kind of generally estimating and then using process of elimination. So take maybe 2 minutes or so, take a look at these 5 scatter plots, these 5 correlations, and try to identify which correlation goes with which scatter plot. So take a minute or two, look back at the definition of correlation and so on, try to match them up, and then we'll discuss in a couple minutes. Okay, it's been a couple minutes, so let's take a look at these 5. Now, one thing that we can sometimes do if to help if we're a little confused about a scatter plot, sometimes what we can do is we can kind of roughly try to figure out what's about the middle of the scatter plot. Looks like about 10, 10. I can draw a set of axes, horizontal and vertical. And I have quadrant 1, 2, 3, and 4. And I can kind of ask myself, does it seem like there's more data in quadrants 1 and 3 and less in 2 and 4? That would suggest a positive correlation. Does it seem like there's more in quadrants 2 and 4 and less in 1 and 3? That would suggest a negative correlation. Or does it seem that the data is kind of roughly evenly distributed between the 4 quadrants? That would suggest a correlation near 0. So more in 1 and 3, positive correlation. More in 2 and 4, negative, and about all the same, close to 0. And here I think I think most of us would agree that there is more in quadrants 1 and 3 than in 2 and 4. We should have a positive linear relationship here, as opposed to maybe something like this one, the bottom center. Here, if I take what looks like about x equals 10, y equals 8, maybe as the middle. Oh, I guess that's not really the middle, maybe 10 or so. That's more like the middle of the data. And here it looks like there's about the same amount in the first, second, third, and fourth quadrant. And also I can see that if you had to draw a line through this data, it will be hard to find a line that models most of the data for this bottom center one. But for the top center one, I think a line like this would do a decent enough job. I mean, there's a point here or there that maybe doesn't fit too nicely, but for the most part, if I can find a straight line that goes pretty close to most of the data. Not really so for this one, right? Any straight line that I draw is going to be pretty far away from a lot of data points. Okay, so I think bottom center is the 0 correlation. And then I have 2 positives and 2 negatives. Well, pretty clearly the top center and bottom right are the 2 positives. And the 2 on the left are the 2 negatives. So if I have a positive linear relationship, what does it mean to have a stronger linear relationship? It means that it looks more like a straight line. So the 0.96 is going to associate with the bottom right because that's very close to a straight line, where the 0.8 is going to associate with the top center because that's kind of like a straight line, but we do have some points here and there that deviate pretty substantially. And then for the negatives, similar idea. Both of my graphs on the left, it looks like we'll have a negative linear relationship, but the one on the top is much tighter into that straight line, that nice linear model, than the one on the bottom left. So the top left is going to be that negative 0.98, very strong linear relationship, but in the negative direction. And the bottom left is going to be negative 0.74. Okay, any questions on correlation? All right, when we come back next time, we will talk about regression. We'll go through some examples in Excel. And the quote of the day today, which I forgot to mention, is be cognizant of assumptions. In a crash, correlations go to 1. So this is kind of a quote that I like to say. There's this idea of diversifying your assets. Like when you buy a stock portfolio, we want to buy a whole bunch of different stocks so that you don't put all your eggs in one basket. And the mathematics behind that really relies on when you have lots of different assets, they're mostly going to be uncorrelated. So if one stock goes up a whole bunch, you'll probably have another one that goes down a whole bunch, and they kind of even themselves out that way. The problem is that if you do that, and it's not so much a problem, but it's just a thing to recognize that if you do that, you're giving away upside, because when you have a big winner, it's probably going to be counterbalanced by a big loser. So you're giving away some upside potential. What are you getting for that? Well, you're hoping to get downside protection. You're hoping that, I didn't choose just the one stock that was the big winner and have a really good day, but I also didn't choose just the one stock that ended up being the big loser and have a really bad day. The problem is that in a crash, correlations go to 1. Not literally, but they get much closer to positive 1. When the whole market is going down, like pretty much everything becomes less valuable, except maybe things like gold and some other things, or options on the VIX or something like that. So it's important to note that a lot of times these correlations are not constant over time, particularly if we're in, say, the financial world or something. So that's something that's, I think, worth noting. So we always want to be careful about our assumptions. We want to understand when the results of our model apply and when they don't. And that's something, people say, oh, modern portfolio theory, it's a great idea. And it is, it's really a good idea. But if you ask your financial advisor who's telling you that diversifying is always good, if you say, why is it good? They'll tell you something from modern portfolio theory, but one of the assumptions is that correlations are constant in time, and that just is not true. So it's something to realize. You're paying a little bit more for that insurance. You're sacrificing more upside than you're getting protection downside. That's a cost, but just like normal insurance in your car or house, that's a cost that you get real value for. So I'm not saying it's not worth it, but it's worth thinking about.